Okay, so the plan today is there's actually one more problem from 3.5 that we didn't quite get to. Um, so just to knock that out, that'll finish up chapter 3 on applications, and then start chapter 4 on graphs. So on Blackboard there's a new tab called supplemental material. There's a supplement on the graphing tool. The graphing tool can have a little bit of a learning curve to use. So that PDF goes through some examples and kind of shows you how to use that graphing tool on WebAssign for the homework. And then just start into 4.1 and 4.2. So that's the plan for today. And then next time we'll just continue on with chapter 4. The quote of the day today is from a YouTuber named Alec Watson. He has the channel Technology Connections, and most of his videos are about kind of the ingenious engineering of kind of common everyday household objects. So things like, a coffee maker, how does it work? And when you start thinking of all of the criteria they have to meet, there has to be cheap, reliable, safe, easy to use, fairly simple so that it's not, complicated to put together, or so it's not breaking down all the time. Um, there's often a lot of uh, ingenuity in the engineering of these just simple objects. Um, so that's usually what he talks about. But this one, this video he posted this past weekend was a little bit of a different one for him. He was talking about how we interact with AI. So not so much about the technical side of how AI works or anything like that, but particularly how we interact with AI, and more specifically how we interact with these recommender systems, these things that say, pick the next video for you to watch, or the next post for you to view, or the next news article for you to read, whatever it may be. And they say, hey, clicked on these kind of things. What about, do you like this thing? What do you think about this one? And I thought this quote by him was a really relevant one to the times that we're in with AI everywhere. I'm not one of these people who thinks that AI is going to take over the world in 5 years and like destroy all of us, but I think it is, like any tool, it can be used in a healthy way or an unhealthy way, and it's becoming more evident that we need to be a little more careful to use it in a healthy way. So this quote from him, succumbing to algorithmic complacency. So that was kind of the phrase algorithmic complacency that he chose to use to discuss this idea of the fact that not only are we okay with these recommender systems recommending things to us, but we actually prefer that. If we had a choice between, you know, searching for a topic that we thought of and looking for a video on it, or going with, whatever the system recommends to us next, a lot of us would actually even prefer just letting the system kind of direct the experience. So succumbing to algorithmic complacency means you're surrendering your own agency, your own essentially ability to make choices, or in maybe some deeper sense, your own humanity in ways you may not realize. And as the internet and real life continue to blend together, I think that's something that we're experiencing more and more, that the real physical world, the way we interact with it, and the way that we interact with the internet are blending more and more. As they continue to blend together, that can end very badly. Today's internet is shaping how we view the world and how we operate within it. We're largely no longer in control of what we see. So I think it's just a bit of a cautionary statement that, um, you know, we need to realize that when we use these AI tools, they can take some of the burden off of our brains. And so some automation is great. If we are not careful, though, we might start automating the things that we really ought to keep kind of to ourselves, though, that we really ought to, where we really ought to maintain that agency, maybe. So just being careful about what we choose to automate and what we choose not to. So just, for example, in YouTube, I almost always use playlists. I have certain people I subscribe to. I go to my subscriptions page, I add videos I find interesting to playlists, and if I want to watch something, I go to one of my playlists and choose from there. So I don't particularly like the YouTube recommendation system, because I feel like it has the primary goal of just keeping me watching things, which usually means showing me things that are going to get me riled up or emotionally uncomfortable or something like that. And that's the way it, seems, at least to me, to foster engagement. So anyway, that's kind of the thought for today. Usually I try to pick quotes that are a little more abstract or philosophical or something like that, but I think this was a timely one, and I liked his idea here that we're giving up our humanity when we're allowing too much automation of these kinds of things. Okay, so our first the first order of business today is to wrap up chapter 3 with one more exercise on 3.5. So last time, I think at the end, we did a few practice examples. We have one more exercise here. So we'll take about maybe actually about 8 minutes or so on this one. And again, this will be kind of similar to the end of last time, that we're going to take a good chunk of time. And at this point, we should be pretty comfortable with these uniform motion applications, these distance equals rate times time applications. So maybe take about 8 minutes or so. Again, read through this on your own, draw a schematic, get an idea of what's going on. Try to work through the problem start to finish on your own without referring to notes or anything like that, as if it was a test, just to get a feel for how well you really have mastered this material from 3.5. If you do get stuck, if you get to a point where you really have no idea, well, then maybe look back at the section 3.5 notes and see if there's a problem that has maybe a similar feel to it or something like that that you can refer back to and get an idea how to approach this. So we'll take I guess about 8 minutes. I'll give you to go through this, and again, treat it as much as you can like an exam problem, unless you get really stuck. But if you get a little bit stuck, try to work through that, right? That's when you learn the most. Um, think of things like, um, what what do I know? What don't I know? Maybe units. I mean, the units here I think are pretty straightforward, um, but yeah, so think of some of those tricks that we had talked about before. And like I said, if you get really stuck, maybe refer back to the previous example, or of course you can always pop a note in chat if you get stuck. And then after about 8 minutes or so, we'll come back and we'll work through the problem start to finish. So I won't write up little notes as we go along, because really the idea of this exercise is to kind of practice for an exam situation. So I want you to have a good assessment of where you're at right now, rather than kind of, me helping you get unstuck along the way. All right, so about 8 minutes, we'll come back and discuss this exercise. Okay, we'll take about 1 more minute. So 1 minute warning. Okay, let's take a look at this one then. I actually didn't get any messages in the chat, so hopefully that means that everybody felt fairly comfortable or was maybe able to, if you ran into a problem, you were able to look back in your notes and kind of work it out yourself. Hopefully that's what that meant. Um, Hopefully that doesn't mean that, you didn't have your coffee this morning and you kind of fell asleep at the computer. Um, but if you have questions that we're going through, definitely feel free to speak up and ask. Okay, so we have two friends, Robert and Sasha. They're walking in opposite directions around a marsh that has a 9-mile perimeter. If Robert walks twice as fast as Sasha, how fast does Robert walk if they meet after 1.5 hours? Now, there is kind of a like brute force, like kind of gut feeling-y way to do this. And I think maybe we'll talk about that after we do it the algebraic way. So let's draw a schematic. We have a little marsh kind of thing here, and the circumference is 9 miles. I'll just kind of draw it with a little circular arrow like that. That's the circumference around. We have two friends, Robert and Sasha. Let's say they start here, and maybe Robert walks one way, Sasha walks the other way, and they meet somewhere along the way. So maybe they end up meeting, or well, Robert's walking twice as fast as Sasha, so maybe they meet somewhere like there. We don't know what that location is that they meet, but we know that they meet there 1.5 hours later. And we also know that Robert walks twice as fast as Sasha. We want to know how fast Robert walks in this scenario. Now, so we have kind of a picture, a drawing. Can we make a more abstract schematic? I actually think if we do this, I think if you see this, uh, this schematic, this is going to trigger something. You're going to say, oh, wait, yeah, I saw how to do this before. Really, I mean, Robert and Sasha are starting from the same point, but they're going in opposite directions. There's little difference between this kind of a setup mathematically, and if they started at two different points 9 miles apart, two different, say, ends of a road 9 miles apart and walk straight toward each other. I think we can see there's little difference, abstractly speaking, between those two. Of course, they could like shake hands at the beginning here, and if they were 9 miles down the road, they couldn't shake hands. But as far as the characteristics of the problem we're concerned with, we can visualize this problem just as though Robert and Sasha are 9 miles apart, and they're going to meet at some point, star, in between them. This feels a lot like I forget their names now, but the two sisters who were meeting at the third sister's house. The two sisters lived such a distance apart. We didn't really know how far the third sister lived from either of the two sisters, but we knew how fast one of them drove relative to the other one, and we knew, I think, the total amount of time it took them to get there or something like that, right? So this has the feel of that kind of a problem. So I know that at the end of this 1.5 hours, Robert will have walked a distance. Let's call it d subscript r. We'll use subscripts here because we want to use distance equals rate times time. So I want to use d, little r, and t to represent those quantities. So then I'll use subscripts to represent, whether we're talking about Robert's or Sasha's distance or rate. And Sasha will have walked distance, Sasha, d subscript s. How much time will it have taken each of them to do that? Well, the time is 1.5 hours for both of them. And what are their rates? What is their speed? Rate little r for Robert, big R, and rate for Sasha, little r subscript s. And something that I kind of see is that the distance that Robert walked plus the distance that Sasha walked has to equal 9. The sum of their two distances equals 9. And that's not just because of this schematic, but that makes sense up here, right? If they start at one point and walk in opposite directions around the figure, when they meet again, they'll have covered the entire perimeter of that in this case, marsh. That's 9 miles. And I also know just directly from the problem that Robert walks twice as fast as Sasha, so the rate for Robert is twice the rate for Sasha. So here I have two equations, but I have kind of two concerns here. One, I haven't used my time of 1.5 hours anywhere. That seems like that should be important. And it's always possible there's an extraneous piece of information in a problem, but that does feel important, right? If they covered the same ground in 6 hours, if it took them 6 hours to meet up, I think both of them would be walking slower, and that would affect the answer to our question. So it seems like the time should be important. We also note that we have two equations, but they're not in two unknowns. It looks like we have basically four unknowns, the two distances and the two rates. But I can connect the distances to the rates using distance equals rate times time. So oh, that should be a capital R. So the distance for Robert is going to be the rate for Robert's speed times the time. Well, that's just 1.5. I see my 1.5 is in hours, and my distance is in miles. So Robert's rate is going to be in miles per hour. And the same goes for Sasha's rate. Sasha's distance is ds. It's going to be Sasha's rate, rs, times Sasha's time, which is the same amount of time, 1.5 hours. And I can keep the second equation just the same. Rate for Robert equals twice the rate for Sasha. And now I do have two equations in just two unknowns, Robert's and Sasha's rates, their speeds. I can solve by just substituting in 2rs for rr. So I have 2rs times 1.5 plus 1rs times 1.5 equals 9. I have 2rs times 1.5s plus another one of those same things. I have 2 apples plus 1 apple. That's just 3 rs times 1.5, and I'll put that 1.5 out front. Or that's 4.5 rs equals 9. Or we see that RS is just 2 miles per hour. Now that gives us Sasha's rate. Our question is, how fast does Robert walk? What is Robert's rate? Well, Robert's rate is simply twice Sasha's rate. So the rate for Robert is twice Sasha's rate, or 4 miles per hour, and that is our answer. Note that we got to the answer and we don't know how far each of them traveled, or we don't know where they met along this line or around this pond. We didn't have to find that. We could find that now if we wanted to. We could see that Sasha walked 2 miles an hour for 1.5 hours. So the distance for Sasha was 3 miles, and the distance for Robert, 1.5 times 4 is 6 miles. So we could come back, and if we wanted to find those distances, we could, but we didn't need to find those distances to get the answer here. Now, what's the kind of gut feeling here? What's the kind of shortcut approach? I can actually make use of something specific to this problem. Now, if I said that, Robert traveled for 3 hours and Sasha for 1 hour or something, and gave a little more information, I might not be able to use this. But because they both walked for the same amount of time, I can basically, I can almost think of like, after a certain amount of time, Robert's covered some distance and Sasha's covered some distance. So the distance that they're moving apart from one another. So I can almost think of like my continuum like this, and Robert and Sasha are like, they're almost like facing off like a duel, or I guess that's the opposite of facing off. Robert's going this way, Sasha's going that way, with rates RS and RR. So actually if I look at the distance between them at a certain time, the distance between them is going to be, well, rate times time, but the rates are just additive. It's just RR plus RS times time. And they meet up on the other side of the marsh when this distance is 9 miles, when they've covered that whole perimeter 9 miles. They meet up on the other side of the marsh when they've covered 9 miles, but that's whenever the time is 1.5 hours later. So their combined speed, if I add their two speeds together, this would be like them walking back to back. This schematic is a little closer in some respects to the original problem. Well, when I add their speeds together, let's just call this R, the sum of their two speeds. Well, 1.5 R equals 9 tells me that the sum of their two speeds has to be 6. Robert's twice as fast as Sasha, so Robert's speed has to be 4 and Sasha's 2, so that they sum to 6. So we could take this approach, and in some respects, this it's simply a different approach. It relies on this fact that they both traveled the same amount of time. And we know what the total travel distance was and the total travel time was. If they were traveling different amounts of time, Robert's going to like stop at some point and Sasha's going to be, keep walking, or vice versa or something. Well, then this kind of a scenario wouldn't really work. But since they were traveling both the same amount of time, I could approach it really kind of either way. So basically we're saying if they meet 1.5 hours later on a 9-mile pond, the combination of their speeds must be 6 miles an hour. for them to, as a combined between the two of them, cover 9 miles in 1.5 hours. So the combination of their speeds, the sum of their speeds has to be 6 miles an hour. This was the algebra. But if you were just to take a gut feeling approach, I think this would be the clearer approach. And then knowing that of that six, 2 parts go to Robert and 1 part to Sasha, that's got to be a 4-to-2 ratio. Okay, so again, at this point, this was kind of an exercise that's meant as an assessment, that's meant for you to see how well you mastered the chapter 3 material. I know word problems are challenging, and that's why I wanted to take a little bit of extra time at the end of last class and at the beginning of this one to work through a couple of these. Are there any questions on chapter 3? All right. Moving on then to chapter 4 on graphing. Again, remember that graphing tool supplement is on Blackboard, so you can go ahead, you can download the PDF and put it on your desktop if you want for, say, quick reference, or you can always find it on Blackboard. So there is a little bit of a learning curve on those, the graphing tool on WebAssign, so I do recommend going on and getting that supplement, taking a read through it. It is like quite a few pages long, but there's a lot of pictures, which is why it's so many pages. So don't think that it's like, you have to read a 30-page document of prose. It's, I forget how many pages it is, but it's a lot of pictures. It's like, do this step, and then it shows a picture of what it looks like, or several different, types of graphs that you might want to construct. All right, so moving into graphing. So what's the idea of graphing? So up until this point, um, anytime we've drawn a picture, we've drawn kind of a schematic diagram like this. But for the most part, we've just worked, like we saw here, with algebra, basically with numbers. We have multiple ways of representing relationships between variables or between numbers or whatever. One is algebraically, like something like this. The relationship between two variables, say Robert's rate and Sasha's rate. We have another way that could be like tabularly. We can make a list of possible speeds for Robert and given speeds for Sasha. If we know that one is double the other, if Sasha's speed is 1 mile an hour, Robert's would be 2. If Sasha's is 2, Robert's would be 4, 3, 6, 4, 8. But there's no reason that we couldn't have, say, 1.5 and 3, or even like pi and 2 pi or something like that. So we could make a list, a table, kind of a numerical descriptor where we take some sample values for, say, one of the variables and see what the associated value is for the other variable. We could also represent this relationship like this in words with some of these, especially the simpler word problems. Like, for instance, think back to the percent applications. Quite a few of those were a pretty one-to-one correspondence between these words and moving right into the mathematical equation, the algebraic structure. But often it's really, really helpful to be able to use a visual technique to somehow visualize a relationship between two variables. And that's what we're looking at here. We've seen a little bit of this already with the idea of a number line and visualizing where numbers land in the number line. But now we're kind of thinking of a two-dimensional rectangular coordinate system, as it's called, where we have two variables. Typically, we use X and Y here, and typically we put X on the horizontal axis and Y on the vertical axis. So we have two variables, and we're trying to somehow describe their relation to one another. Again, we could describe that relation maybe through words, or maybe through an algebraic structure like an equation, or maybe through a list of values, a table of values that show the different different possibilities for that relationship, or we could use a graph. And that's going to be the focus of chapter 4. And one of, I think, the most powerful and maybe like least explicitly appreciated uh, abilities in mathematics is the ability to move between the algebraic structure and the graphical structure seamlessly. Sometimes for some problems in some scenarios, it's better to look at the algebraic structure. That that path is a little more clear in a sense. And sometimes the geometric or the graphical structure is the way to go. That makes things a little more clear. So if you kind of start stumbling in the algebraic side, being able to jump over to the graphical side for either some inspiration or clarification or to move forward in the problem, that's a very valuable tool to have. So that's what we're starting off our discussion with here. We're trying to work up to the point of that fluency between algebraic structures and graphical structures, and we're introducing our rectangular coordinate system. Sometimes this is called the Cartesian coordinate system, named after Descartes, Rene Descartes, the French philosopher, famous cogito ergo sum. I think, therefore I am. So sometimes called the Cartesian coordinate system after him, sometimes called the rectangular coordinate system, but or often just called the coordinate system or the plane because it's you know it's kind of the default one that we use. Okay, so what is on this plane? Well, we have two variables, x and y, and essentially what we have is two number lines. If I forgot about everything, this, if I forgot about all of this stuff here and just got rid of it, and I focus just on this bit here, I actually recognize that that's just a number line, right? We start at 0 and we go to the right, 1, 2, 3, 4, to the left, -1, -2, and so on. That's kind of a number line related to the variable x. So this horizontal line here, this horizontal axis, we call it, this horizontal axis is really just a number line that's related to whatever variables associated with that, which we typically call x. By default, that variable is going to be x. And then likewise, we have what amounts to another number line. If we just focus on this vertical line here and forget about everything else, we see we have to tilt our head a little bit, but again, we have like a 0, and then going up, we have 1, 2, 3, and going down, we have -1, -2, -3. This is like just another number line that intersects the first number line. We call this our vertical axis. And again, by default, it gets the variable name y. So y goes with the vertical axis, x with the horizontal axis. Now, a little side note, sometimes when I'm not being careful, I mix up horizontal and vertical, and I don't know why I do that. There's a couple of things like Star Wars and Star Trek. My wife always laughs that I consistently get them backwards. It's not just like I get them backwards every once in a while, but consistently I get them backwards. So if I mess up and, I'm trying to be careful when you say horizontal and vertical correctly, but every once in a while I get it a little bit backwards. But just, just give me a holler in the chat if I said it backwards, and I'll correct myself. But so yeah, our horizontal axis, the flat one, is associated with the variable x, unless very explicitly specified otherwise, and our vertical axis associated with the variable y. And we see it's the intersection of two number lines, and that intersection occurs here. It occurs at the 0 point on each number line. So I match up the 0 points. So I take the point on the Y number line, the vertical one, where there's 0, and the point on the X number line, the horizontal one, where there's 0, and that's where I choose the intersection to be. So when X equals 0 and Y equals 0, there's a special name for this. It's called the origin. It's kind of, in a sense, where all other points on the plane on this coordinate system are measured against. Now, if I look at this plane, when I'm plotting a point on this plane, if I plot, say, a point here, I see that this point is associated with X equals 2, Y equals 4. Right, I can refer to the horizontal number line and see that that point is 2 units to the right horizontally from the origin. So it's 2 units over on the X scale, and it's 4 units up vertically from the origin. It's 4 units up on the Y scale. We see that this plane has some Roman numerals here. It has these 4 quadrants. Typically, these Roman numerals are not explicitly written on the plane. We're just writing them here for demonstration. So these are the quadrants 1 through 4. We notice in quadrant 1, X and Y are both bigger than 0. Quadrant 1 is the corner or the quarter, however you want to say it, of the plane where my X numbers are positive and my Y numbers are positive. I'm at 1, 2, 3, 4 on X, but also positive numbers on Y. And then I go around counterclockwise. So my quadrants are labeled counterclockwise. And if you've had some exposure to, some slightly more advanced math, things like trigonometry, if you've seen anything related to that, you know that when we talk about angles, if I had a line going out from here and I was looking at the angle, it's kind of measured from this positive x-axis going counterclockwise. So there is a somewhat good reason for the quadrants being labeled counterclockwise. So we don't label them like the way that we would like read a book, like top left, top right, bottom left, bottom right, or something like that. They're labeled in this manner. We see in quadrant 2, this is where X is negative and Y is still positive. In quadrant 3, well, here both of them are negative. And quadrant 4, X is positive, Y is negative. So we have these 4 quadrants. Again, starting at the quadrant where both of them are positive, that's what we label quadrant 1. And we proceed counterclockwise around to quadrants 2, 3, and 4. Okay. So now let's look at this example. Trying to get this. I think that's close enough to, I don't have the whole graph on the page, but I don't think we will need that very bottom little bit of it. As an aside, if you want to, you can buy a notebook that has like graph ruling. So it'll have, pages that basically look like this. And if you want to buy one of those, you can, but you don't really have to. You can get away with just drawing yourself a couple of axes and doing what you need to do on those axes. So you don't need to draw out this entire grid every time that you do a graphing problem. The grid can sometimes be nice to have, and I'm using it here so that it makes it a little easier for you to see on your screen kind of where everything is tracking. but it's not really necessary. Okay. Okay, so let's take a look at this. Let's plot each of the following points on the Cartesian plane. So here we have something like this that almost looks like an interval. It almost looks like I'm saying, 0, comma 1, going from 0 to 1, not including either end. For this notation, context matters. So the point, let's say 6, comma 4, our first one here, what does this notation mean when we're in the context of a point on the plane? So what does this context mean? Well, this refers to the two coordinates, the x coordinate and the y coordinate of a point that's located on the plane. So this is kind of the numerical representation of a point that's visually located somewhere on the plane. Where is this point located? It's located at x equals 4. Remember, my x-axis is my horizontal axis, and y is the vertical axis. Oh, x equals 6. I looked at the wrong number. X equals 6. My x-axis, my y-axis, and y equals 4. So I want to ask what point on the plane would be associated with an x value of 6 and a y value of 4. That would be, if I go up from 6 and over from 4, that would be this point here, 6, comma 4. Now, often we don't explicitly label our points. So usually we would just plot the point there like that and be done with it. But I will label them just because we're, getting a little more practice at plotting these points. So 6, comma 4, x equals 6, y equals 4 refers to that point on the plane. What about negative 2, comma 5? Here we're looking at x equals negative 2, y equals 5. So we're referencing that point when we say negative 2, comma 5. Or negative 3, comma 8, x equals negative 3 on the horizontal axis, 8 on the vertical, negative 3, comma 8. I'll check them off as I go along. What about negative 7, comma negative 1? So on the horizontal axis, negative 7, going vertically down 1 to negative 1. That is negative 7, comma negative 1 in the third quadrant, because both of the coordinates are negative. Okay, yeah, that's just responding to the chat message. Yeah, that's not a problem. If you're having internet issues, you can definitely watch the recording later on YouTube. Yeah, not a problem. So 6, comma 6. Here we're looking for 6 on the horizontal axis. And then instead of going up 4 like we did for our first point, we're going to go up 6. So 6, comma 6 located there. What about something like 8, comma 0? I want to be at location 8 horizontally, so I want to be associated with x equals 8. I want to be somewhere kind of on that line, somewhere above or below x equals 8, or actually in this case, because I'm looking for y equals 0, remember the origin is when x equals 0 and y equals 0. So 8, comma 0 means I'm at 8 on the x-axis and 0 on the y-axis. I don't deviate vertically up or down. I'm actually right on that x-axis at location 8. So this is 8 comma 0, x equals 8, y equals 0. Analogously for 0 comma 1, when x is 0, I'm thinking of going vertically up and down some amount of distance from this x equals 0 point here. And I'm going up to y equals 1. So this is 0 comma 1. And then lastly, 0 comma 0 is our origin. So we have some points that are in one of the 4 quadrants, like these 2 points are in quadrant 1. And we have some points that are on the axes, on either the x-axis or the y-axis. And we have a point that's at the origin. Okay, let's go through an exercise. Maybe take about maybe about 2 minutes or so. This shouldn't take very long. And plot these points on a graph. And again, if you don't have graph paper, you don't need graph paper. We could have drawn our own graph. I'll just draw tick marks 1 unit apart. So here's 3, here's 6, here's 3 and 6. And if I wanted to plot 6 comma 4, I'd go to 6 on x, go up 4, and it's going to be about here. It's going to be a little less accurate because I'm kind of guessing the horizontal and vertical positions, or 6 comma 6. Maybe here again, I'm kind of like imagining tracing a line over horizontally, like parallel to the x-axis. So it's going to be a little less precise, but you can certainly get the job done with just drawing your own coordinate axes like that. If you want something a little more precise, a little more neat and tidy, like I said, you can get graph paper, or if you wanted, you could, I'm sure there are all kinds of sites online that have, just a, a Cartesian plane like this. You could go and you can print some off to use. But you don't need that, so you can just plot each of these points on a plane of your own making if you want to. Okay, so take about 2 minutes or so, plot each of these, and we'll come back and discuss. Okay, it's about 2 minutes. So I went through a couple of them as we were working through them. So we see -3 comma -3. Here x equals -3, y equals -3. So we're down here in our third quadrant when both of the variables are negative. 4 comma -1 is over here in our fourth quadrant when x equals 4, y equals -1. So we go to the right 4, down 1 from the origin, taking us to 4, -1, or 6 comma 0, we go to the right 6 units, and we don't go up or down any units from the origin. That puts us at this point that's on the x-axis, 6 comma 0. And filling in the rest, 3 comma 2, we go to the right 3 and up 2. We see this is at point 3 comma 2, where x equals 3, y equals 2. -5 comma 7, we go to -5 on the x-axis, and then we go up to 7 on the y-axis. 0 comma 2, we deviate horizontally 0 units from the origin, and we go up 2. That takes us to this point on the y-axis. And then lastly, 0, 0, just the origin itself. We don't deviate any amount horizontally or vertically from the origin. Any questions on this one? Okay, so now let's do this in reverse. Let's take a look at each of these points. We see there's 1 point in the first quadrant, 2 in the second quadrant, 1 in the third, 2 in the fourth. Let's take a look at each of these points and label the name of their point. Maybe I'll do it in red since it's just a little easier to see. So if I look at this point in the first quadrant here, oh, I feel like I'm doing modern editing here with jump cuts. Sometimes when I undo, it undoes my writing and then like jumps me back to where I was before I scrolled, before I wrote somewhere. So, but anyway, so if we look at this point in the first quadrant, we see that it's associated with the x coordinate 3 and also the y coordinate 3. I might jump again. All right. So we see this point we can label as 3 comma 3. Let's proceed to the second quadrant, these ones over here. So in the second quadrant, we have negative x values with positive y values. So our first coordinate should be negative, and our second coordinates should be positive. So if I look at this one that's the higher of the two, I see that's associated with x equals -5 and y equals 7. Or the other one associated with x equals -7 and y equals 2. Right. So again, by convention, our horizontal axis we typically call x, vertical y, unless explicitly stated otherwise. And our horizontal component always goes first, and our vertical component always goes second. That's just a notational convention. There's, as far as I know anyway, not a good reason for that order. It's just that's the order that we had to pick an order, and that's the order that was chosen. So that's how it works. Going down to our third quadrant, we see in our third quadrant both coordinates will be negative, and indeed we see x equals -1, y equals -5, -1 comma -5, the label for that point. And in our fourth quadrant, we see over here x equals 6, y equals -2. That's the bottom right of the 2 points. And actually, the other point is something we might not have seen yet. But these number lines are continuous, right? I mean, I have tick marks at 1, 2, 3, 4, 5, but that doesn't mean that those are the only allowable coordinates. I could have coordinates between them. It's a little bit like longitude and latitude lines, right? Like we have these lines, however many degrees of longitude and latitude on the globe, but there are certainly places that are not directly on one of those intersections. And that's what we see here. We see that it looks like the x coordinate, the horizontal coordinate, is between 4 and 5. It looks like about 4.5. So my first coordinate I'll call 4.5, and my second coordinate -1. Right. So one thing to note here is that anytime we're dealing with a visual representation, there's always going to be some margin for error, right? We can never, so if I say something like something algebraically like, R equals 2s, that's a very specific statement with zero error in it, at least as it stands, as an algebraic statement. But we see when I give you a set of or when I give you a set of coordinates and I ask you to plot the point, you're not going to be able to plot it perfectly at the correct point. It's going to be hopefully close enough. Or when I give you a point and ask you what coordinates is it at, could this -5 comma 7 really be like -5.01 comma 6.98? Yeah, maybe, right? But we're looking to get pretty close. This 4.5 comma -1, pretty clearly that x value is not 4 and not 5. It looks like it's about right in between them. Could it be, 4.47 or something like that? Yeah, maybe, but it's going to be pretty close to 4.5. So right there's always a bit of a question here about tolerance. How much error are we willing to tolerate in our plotting of points or in our interpretation of points that have been plotted? And that's dependent typically on the scale that's given, as well as, just the general context. Okay, so just like above, let's do an exercise. Again, we'll take maybe just about a minute or so for this one. I'll just work through it with you. State the location of each point in ordered pair notation. So there are 4 points here, one in each of the 4 quadrants. So I'll just go along with you. Quadrant 1, 2, 3, 4. I'll give you about a 15-second head start, and then I'll just start working through them as well. Okay, so these are the 4 sets of coordinates that I got. For the quadrant 1 point up here on the top right, we see that's associated with, oh, no, okay, that's right. I thought I labeled it the wrong number, but I didn't. That's associated with the horizontal value 3 and the vertical value 8, so that's 3 comma 8. The quadrant 2 number on the top left, or quadrant 2 point on the top left, is associated with the coordinates -8 comma +8. And quadrant 3 on the bottom left, -6 comma -2. And quadrant 4 on the bottom right, 2 comma -2. Any questions on those? Okay. Okay, so let's take a look now. We're going to shift gears a little bit. We're moving back to algebraic structures for a time here. And then we're going to try to marry these two ideas together. Let's take a look, not really a first look, but kind of reminding ourselves of how equations in 2 variables work. Our linear equation can be written in standard form, ax plus by equals c. So here, note that we've combined all of the x terms together on one side. We've combined all of the y terms together on the same side as the x terms. So all the variables, x's and y's, are on the same side. And then equals c, we've combined all the constant terms together on the opposite side from the variables. There are kind of a couple of different standard-ish ways to write a linear equation, but this is what's called the standard form. So there's, for instance, like slope-intercept form. That's another form that can be useful in some contexts. But that's not what we're discussing here. This is called standard form. Ax plus by equals c, where a, b, and c are numbers, and x and y would show up as variables. So if I look at this example, y equals 7x minus 4, this has some x terms, some y terms, some constant terms, but they're kind of jumbled about, right? The variable terms are split between two different sides of the equation, and this variable term is jumbled up with a constant term. So let's put this in standard form. And I think the easiest way to do that, I noticed that if I move my x term to the other side, my x terms and my y terms, or just my one x term and my one y term, will be on one side, and then my constant -4 will be on the other side, and that's what I want for standard form. I can achieve this by subtracting 7x from both sides, and I get -7x plus y, or plus 1y. So here b equals 1, equals -4. And this would be my equation in standard form. One kind of interesting thing to note is you might say, well, what if I wanted to move my y to the right-hand side? Say subtracting y from both sides. Well, that would give me 7x minus y minus 4 on the right-hand side. So I'd also need to get rid of the 4. I need to move the 4 to the other side. And this would give me 4 equals 7x minus y, or flipping that around, 7x minus y equals 4. Well, that's actually just as valid of an equation. My a, b, and c have just all changed sign from, positive to negative, or negative to positive. So, the standard form of a linear equation isn't quite as unique as we might expect it to be. But, these two are just off by basically multiplying both sides of the equation by -1. Or if I multiplied both sides of this equation by, say, 2, I would have another linear equation that would be in standard form. So these are different representations of really the same underlying structure, and we probably could call all of them standard form. Okay, again, what about this exercise? Convert this linear equation into standard form. Well, here my left side has a variable term and a constant term. My right side, just the variable term. Maybe I'll just subtract y from both sides. To get 5 equals 2/3 x minus y. And I can see if I just swap the sides of the equal sign, I can see very clearly that this is in standard form. Note that a, b, and c are real numbers. They could be integers like they were up here, but we can have a fraction, we can have a decimal, we can even have irrational numbers like, say, square root of 2, or even transcendental numbers like pi, something like that. These can be any real numbers, these coefficients for x and y and the constant. If we wanted to, we can multiply everything by 3 to get, say, 2x minus 3y equals 15. that might be a nicer, cleaner version to work with, practically speaking, right? Just because all of my coefficients are integers now, it's maybe just a little easier for me to work with. Now, if I have a relation like this between two variables, I have an equation relating x to y. This is a little bit like, saying that whatever it was, Robert's speed is twice Sasha's speed. If Sasha's speed was 1 mile an hour, then Robert's has to be 2 miles an hour. If Sasha's speed was 10 miles an hour, Robert's would have to be 20. I have two variables, so two things that in essence can be chosen freely. I could plop a point down kind of anywhere I want. I can choose my X and Y coordinate kind of any way that I want, uh, just initially on my graph here. But this equation represents a constraint. It's a claim about the relationship between X and Y. It's one constraint. And often if I take the number of variables minus the number of constraints, that's the amount of freedom that I have, the number of so-called degrees of freedom that I have. So I see I have two variables, two things I can choose, and one constraint on their relationship. That leaves me with one degree of freedom. That leaves me with one free thing to choose. So for instance, if I say in this relationship, y equals 5x plus 1, if I were to say choose x to be 1, I've kind of used up all of my free choices. Now y should be set in stone. What will y be? Well, y is 5x minus 1, 5 times 1 minus 1, or plus 1, sorry, 5x plus 1, and that is 6. So when x is 1, y has to be 6, or that would be associated with the ordered pair, x comma y equals 1 comma 6. So I think now we're starting to see a little bit about how the algebraic structure can relate to the graphical structure by writing this relationship between x and y as an ordered pair. Or in the second line here, maybe instead of choosing x to be 1, scrap that, forget about that. Now we're going to choose y equals 16. What does x have to be? Well, I would have 16 equals 5x plus 1, and we can either just guess a solution to this pretty easily, or we could subtract 1 from both sides and get 15 equals 5x, divide by 5 and get x equals 3. So when y is 16, if we were to pick y to be 16, then we'd have to have x equals 3 associated with it. Or again, scratch that. What if I had picked instead x to be 0? Well, y would have to be 5 times 0 plus 1, or y would just have to be a 1. So we actually see we have three different ordered pairs now, 1 comma 6, 3 comma 16, 0 comma 1. We can imagine that we might want to plot these on our plane and do something with them. We're not quite there yet. We're still working on the algebraic side at this point, but we can I think see where this is headed. And there's nothing super special about x equals 1 or y equals 16 or x equals 0. If you wanted, you could ask this question about, y equals 4 or x equals 7, or right, we could continue fleshing out this table of values if it served us well to do that. If we wanted more points, if we wanted more relationships between x and y, when x is this number, y has to be that number, or vice versa, we could just keep picking different values for x or different values for y, finding the associated value for the other variable, getting another ordered pair, getting another point on the graph on the plot for this relationship. Okay, let's look at this example. 3y plus 6x equals 18. That's the equation under consideration. Again, two variables, one equation. We can pick one of our variables values, but then that constrains what the other variable has to be. So when x equals 0, what does y have to be? We have 3y plus 6 times 0 equals 18. 3y equals 18. Y has to be 6. Or x equals 0, y equals 6 is associated with the ordered pair 0, comma 6. Again, we can imagine maybe going and plotting 0, comma 6 as a point on a graph. Or say when y equals 2. So note that to fill in each line, we're actually solving a linear equation. These aren't super challenging linear equations to solve with parentheses and all kinds of stuff, but nonetheless, we have to solve a linear equation on each line. When y equals 2, I have 3 times 2 plus 6x equals 18. I have 6 plus 6x equals 18. Or I have 6x equals 12. I have x equals 2. So when y equals 2, x has to be 2 as well. And then when y equals 0, 3 times 0 plus 6x equals 18. Or that's just 6x equals 18, or that's x equals 3. So 3 comma 0 would be the associated ordered pair. Okay, let's take a look at two exercises that are similar to the ones we just did. We'll take maybe, let's say, 4 minutes and work through these. And because these are pretty straightforward and they're also a nice review of just some easy linear equation solving, I think we'll take 4 minutes. I'll let you work through them yourself, and then we'll come back and we'll work through them together. So 4 minutes might be a little bit of a time crunch, but I think you should be able to do it. Um, at this point of mastery in solving equations. So about 4 minutes, we will come back and discuss the answers. Okay, it's just about 4 minutes, so I think you should have been able to get through these two pretty comfortably. Maybe you had, one line left to do or something, but should have been pretty straightforward. Um, and again, if you found some of these exercises challenging, like the ones at the end of last time or beginning of today, or these linear equations are taking a little bit longer, maybe go back and drill some of that material a little more from some of the previous sections just to kind of brush up on it a little bit and increase your mastery of it. Um, but we see for the first example, we have when x equals 1, y is going to be 3 minus 1 or 2, giving us the ordered pair 1 comma 2. When y is 14, that means that 14 equals 3x minus 1. So x must be 5. We add 1 to both sides. 3x equals 15, divide by 3. When y is 0, we get 0 equals 3x minus 1. Add 1 to both sides, divide by 3. We actually get 1/3 comma 0. Not a particularly nice point, right? We'll talk a little more about that later, but if I have a nice coordinate system like, or a nice picture like this one, I don't want to try to graph things like 1/3. I would prefer things that are points that are on an intersection between two of my grid lines. So, maybe I would, instead of using y equals 0 and then x equals 1/3, maybe I would toss that point out and use a different point to help me with my graphing, right? Not because 1/3 comma 0 is some kind of fundamentally bad point. It's not that it's wrong. It's a perfectly valid point, but it's just a little more cumbersome and annoying for me to graph than maybe a point that was at an intersection of two of those grid lines. A point that had only, say, integer values might be preferable just for purely practical reasons, right? 1/3 comma 0 is a perfectly fine point in theory, but in practice it might be a pain to graph. And similarly down here, oops, 6y minus 2x equals 12. You might have noticed that if you divide both sides by 2, we get 3y minus x equals 6. That's kind of a simpler equation. It's a little easier to work with. And it's just a rephrasing of that same equation. So we could do that if we wanted a little shortcut, but we'll just proceed directly here. When x is 0, that means that 6y minus 0 equals 12. Y, of course, has to be 2. When y is 3, that means that 6 times 3 minus 2x equals 12. 18 minus what has to be 12? Well, that's got to be 2x has got to be 6, or x has got to be 3. So when x is 3 and y is 3, I get 18 minus 6 is indeed 12. And when y is 0, I get 6 times 0 minus 2x equals 12. The 6 times 0 is just 0. X is 12 over negative 2, or negative 6. So negative 6 comma 0 for that ordered pair. Right? Again, at this level of mastery with equations, none of these were super, long or complicated equations with fractions or having to, distribute and simplify and get variable terms together and all of that kind of stuff. It's, uh, they started off in pretty nice form, either in standard form or in, not quite standard form, but still pretty nice to work with. So these should have gone pretty quickly. Now, quite a few students find it difficult to make this jump. They can do these kind of problems just fine. But then if I say find 3 solutions for this equation, they really don't know where to get started. Well, kind of the nice thing is that you can pick essentially whatever value of whichever variable you want to start with. The downside is, so my wife has this analogy. She's sometimes calls something in the cereal aisle. It's almost like sometimes you have so many different choices that you don't really know where to start. It's almost like you wish that your choices were artificially narrowed so that you could just say, okay, this is the best one, and it would be easier to evaluate the landscape. Okay, so I need to pick, let's say, some value for x and then find the associated value for y, or vice versa. Two good choices to start with are the zeros. So let me start with x equals 0. Before I go and write my answers in over here or start writing them in, I'm going to do my scratch work first because, I kind of in the back of my mind, we haven't talked much about it, but I kind of know that where I'm headed with this, where the graphing section is, that I want to graph these points eventually. So I have an eye towards that strategic idea of, okay, I'm probably eventually going to want to graph these points. I would like to make choices that give me ordered pairs that have integers as their coordinates so that they're easy for me to graph. Again, that's not to say that, ordered pairs without integers as coordinates are bad in some way or like wrong or anything like that. That's certainly not the case. But just practically speaking, they're a little harder to graph. So when x equals 0, well, I notice that y is 8. That's a pretty nice ordered pair. Let's use that one. Another good choice is y equals 0. Well, that means that 0 equals negative 2x plus 8. We can add 2x to both sides and get 2x equals 8, or of course, x equals 4. That's also a pretty nice one. Let's use that. So these are usually two good places to start. Try x equals 0, see what y value you get. If you get a nasty y value, if you get y equals 1/3 or something in another problem, well, just don't use that one. But, in this case, it worked out nicely. And then try y equals 0, see what you get for x. Now we need to find another one. And I probably don't want to use something like y equals 3. I can kind of see that my right-hand side for integer entries is going to be an even number, and that's not going to mesh so well, right? 3 equals negative 2x plus 8. I have 2x equals 5. Add 2x to both sides, subtract 3 from both sides, right? X equals 5 halves. That's not a super nice point to work with. I could I could definitely write it down here and it would satisfy the question, right? This is certainly a solution. 5 halves comma 3. 5 halves comma 3. That would complete the answer to this problem. But again, we're kind of in the back of our mind thinking the real goal of this is to get an ordered pair and then plot it on a graph. Let's try to get one that's a little nicer. I noticed that if I plug in a value for x, this right-hand side, if I pick an integer value for x, the right-hand side will be an integer, and that's just what y is going to be. So in this case, I'll just choose a different integer value for x. I used x equals 0. I've already found the association with x equals 4. Let's just try x equals 1. That's a pretty easy value to choose. Why did I choose x equals 1? Because it's a small number that's not 0 or 4. It's probably going to be easy for me to put in and to do the arithmetic to simplify. So then y is going to be negative 2 times 1 plus 8. 8 minus 2 is 6. So 1 comma 6 is a third solution. Again, this fractional solution here is a perfectly valid solution. You could put that in, hit enter on WebAssign. That would give you a check mark. But if our goal was to find 3 solutions for the equation and plot them on a graph, I wouldn't really want to try to plot 5 halves comma 3, right? It's unlikely to occur at a nice intersection between grid lines. It's going to be a little harder for me to figure out where I should put it. I want to make life easy for myself. So I'll shoot for these kind of integer coordinates when I can get away with it pretty easily. Okay, and since we only have 6 minutes left or so, let's just jump down and do this one exercise. And then next time we'll kind of warm up with this example, this exercise, and we'll continue on from there. So just work through this one exercise. Will take about, oh, let's say about 2 minutes, and then we'll come back and discuss. So work through this exercise 2 minutes, and then we'll discuss the answer. Okay, so let's go through the answer to this one, and then we'll wrap up for today. So we see if we try x equals 0, we get pretty easily y equals -7. Nice integer coordinates. Let's use that one, 0, -7. If we try the other one, y equals 0, well then 0 equals 5x minus 7. It turns out that x equals 7/5. Again, in theory, a perfectly valid solution. Nothing in theory wrong with that. We could write that down here. That would be a valid part of the answer. But with an eye toward graphing, I'd rather have integer coordinates. It's easier for me to graph when I can get away with it. So let's not use that one. Let's try x equals 1. Again, I have just kind of y equals some expression with x. If I plug in an integer for x, I'm going to get an integer out of the right-hand side. So I'll choose to plug in values for x because everything's kind of already solved for y. So x equals 1 yields y equals -2. That looks like a good one, 1 comma -2. Now down here, I tried x equals 5, and you do the ciphering and you get y equals 18. This might seem like a pretty good one, right? I got 5 comma 18, integer coordinates. But another thing to kind of keep in mind is that usually when we're working on a graph, we're kind of working on a picture like this where we have -10 to 10 on each axis. So again, is there anything, where was I? Is there anything fundamentally wrong with 5 comma 18 as a point? No, it's a perfectly valid point, but it's unlikely to be, it's kind of too far astray, right? It's going to be kind of way off, way up high on our graph. And it's probably, if we're dealing with a WebAssign tool, it's probably going to be off of the graph and we're not going to be able to plot it. If we're even graphing by hand, we're going to have to like extend our axis way up high on the vertical, in the vertical direction. I probably don't want to use this one. I'm shooting for x comma y values where my coordinates are integers and probably also between -10 and 10. Sometimes I can't get both of those. Sometimes, it doesn't work out so nicely, but when I can, I'm going to shoot for that. So I see something like x equals 2, y equals 3. That works a lot more nicely. When x is 2, my right-hand side is 10 minus 7, or 3. I'll use that one instead. And this gives me three nice points that I can pretty easily plot on a standard -10 to 10 in both directions coordinate plane and integer coordinates. Okay, so when we come back, we'll knock out this example, this exercise, and continue on. Are there any questions from anything today? All right, then that wraps up our discussion for today. Let me stop the recording.